So by the end of today, the hope is that we understand how to graph polynomials in factored form. We will do a little bit of factoring review, okay? Only like common factoring and factoring quadratics, just as a recap. And then once we get into our next unit, after we're finished this one, we're going to talk more thoroughly about factoring polynomials. So we will know how to determine things in both standard form and factored form. And we'll talk about the different reactions to things when we have a variety of different types of x-intercepts. So the first thing that we need to know when we are graphing polynomials is about orders. So orders of zeros are determined, so when I say zeros, I mean x-intercepts. The orders are determined by the exponent that we see on a bracket with any x, or if I have a single x by itself, the exponent on that x. So look for the exponents. They tell us information about orders. And this is actually going to tell us how the graph reacts at that specific x-intercept. So I'm going to draw you guys some pictures for these, and then we'll look at some examples where we can actually apply this information. Order 1. So order 1 is kind of what we're used to seeing, and that is basically if I have an x-intercept, my graph just goes right through it. So maybe I have something like this, and this is an order 1, 0. Okay, and maybe we'll make ourselves a note that the graph goes straight through the x-axis. Or it might be on a slight curve or whatever, but it goes through the x-axis. I'm not going to say straight, but goes through the x-axis. Okay, order 2. Order 2, I almost think about, it takes like this quadratic shape on. So as it goes toward the x-axis, what it actually does is it sort of like grazes the x-axis, but just bounces right off of it. So an order 2 x-intercept is going to will come towards, hit it, and then bounce off of it. And then whatever happens after that is determined by other things. So this is an order 2, 0. So bounces off the x-axis. Okay, so it still crosses through at that one point, still hits that one point, but it doesn't cross to the other side. So kind of like a quadratic shape happening there. And then order 3 is actually similar to like a cubic shape, and it will sort of go through, so it's still going to go through, but it will go through the x-axis in like an S shape as it goes through. So if I have, this is going to be order 1 over here. If I have an x-intercept that is order 3, it will go through, but in an S shape. So this one is order 3. This one over here, that would be order 1, because it just goes through straight, doesn't do like a curve through it. Okay, so this one goes through, but in an S shape. Okay, so one important thing that you may want to underline or highlight in the little paragraph above is that I can only determine orders on zeros when I'm in fully factored form. Okay, so if we have something in standard form, we would need to take some steps to get that into factored form to see what those x-intercepts are and to see the correct orders on them. All right, so let's take a look at an example here. So we are going to factor if necessary, always, and then we're going to identify some of the key information, so things like degree, end behavior, leading coefficient, zeros and their orders. What we can fill out already now, because we're in standard form here, is we can fill out degree, leading coefficient, and end behavior. So let's start with that. We know how to do that. Okay, I'm just going to use LC for leading coefficient, and end behavior, either notation is fine, whatever you feel comfortable with for this one. And we can also actually fill out Y-intercept for this as well. So I'll fill that in. So usually, if I want to determine these things, especially degree and leading coefficient, I actually do need something in standard form. If it's already in factored form, there's a little trick that I will show you later in the lesson. Or the other option is you FOIL it out to see it in standard form. So what is the degree and leading coefficient here? We'll start with that. Sophia? Perfect, 4 and 1. Looking at this, highest exponent and number in front of it is leading coefficient. What does this tell me about end behavior? Billy? Okay, so I know the ends must have the same end behavior because it's an even degree polynomial. And this actually will tell me information about the right end. If my leading coefficient is positive 1, I know my right end is positive. And because it's an even degree, I know they have to have the same end behavior. So I know they both must be facing up. So I usually just like to sort of draw myself a general picture of what I know the ends are going to be doing. And then I put my end behavior in. So that must mean this goes from quadrant 2 to quadrant 1. And the Y-intercept, I can find Y-intercept pretty quickly in standard form by simply looking at the constant value. And because there's no constant that's visible here, what does that tell me about the Y-intercept? Must be 0. So the graph must have a Y-intercept at 0, 0. Okay, so you can sub in 0 for x and calculate the y, or if you're in standard form, just look at the constant value. But this is like a foolproof method. Like if you just sub in 0 for all your x's and calculate, you can find y-intercept in standard or factored form. Okay, let's get into some extensions here into our new lesson. So I need to factor this. The general rule of factoring is we always, what does this mean? CFF, who's had me before that remembers what I mean when I say this? Lexi? Common factor first, perfect. If you see this on a test, it means you forgot to common factor first. And if you forget this, you make your life unnecessarily hard. Who enjoys making their life unnecessarily hard? Okay, good. You're all sane. That's lovely. I don't want to make my life harder than it needs to be. I'm going to common factor first. I'm going to make my life like 10 times easier. So are there any common factors here? That's the question I want to ask myself to start here. Okay, I'm looking at the numbers and also the variables. Is there something I can take out from all terms? Carol?
The x squared.
I can take out an x squared from every term. Every term has 2 x's in it, so I'm going to remove that. It doesn't disappear into thin air. It just comes out front, and I start a bracket, and I write what's left. Okay, so if I take out an x squared from 4 x's, I'll be left with 2 of them, so I'll be left with an x squared. If I take out 2 from these 3, I'll be left with 1. And if I take out these 2, all that I'm left with is plus 3 now. Okay, so we common factored first, perfect. Now I need to see if I can factor what's in the brackets a little bit further here. This is an easy, we call this an easy trinomial. It has an a value of 1. So when I say that, I mean it has a 1 in front of the x squared. So I should be able to just find the two numbers and put them into brackets right away. What am I looking for when I factor something like this? It needs to multiply to something and add to something. What are those numbers? Multiplies to, Oliver?
Is it multiplies to 3 and adds to
No, negative 1.
I got that wrong, but yeah.
So not negative 1. The 3 is good. Jess? Negative 4, this center term here. Okay, so we need to find two numbers that multiply to 3 and add to negative 4. Okay, we're thinking back to grade 10 and 11 here, just refreshing our memories a little bit. Nicole? Okay, negative 1 and negative 3 fit. What do I do with these numbers now? I want the quick way. Don't take more time than you need on this. I should be able to go right to the factored form. Lexi? Perfect. Okay, soon as I have the numbers, because this is factoring an easy trinomial, I put them right into the brackets with the x's. And now this is in fully factored form. Okay, so now I should be able to identify zeros and their orders. Or in other words, I'm saying x-intercepts, right? Let's find the x-intercepts now. Give me one x-intercept. Somebody out there. What can I determine as far as x-intercepts by looking at this? Oliver?
Is it not like a negative 1 and 1?
Close. Lucas?
Isn't it just 1 and 3?
Okay, so I have positive 1. Remember, we must switch the sign here. 3 is also 1. Anywhere I see an x should produce a 0. So this also produces an x-intercept. What do we get from x squared? Whenever I'm finding an x-intercept, I set the equation equal to 0, and I want to know what x's I plug in here that could make this whole equation equal 0 when I multiply them. Trent?
0.
So the x that I would sub in to x squared that would make that whole equation 0 would be 0. So I also have an x-intercept at 0, 0. This makes sense because I have a y-intercept at 0, 0. If I'm crossing the x and y axis, both at 0, 0, that's an x and a y-intercept. Orders. The orders are determined by the exponents that I see. Either if it's a binomial, it will be on the bracket, or if it's just like a single x term, it will just be what I see on that variable. Okay, so this has an exponent of 1, 1. So these are both order 1. Okay, I know if I don't see an exponent on the bracket there, it's going to be a 1. So both 1 and 3 have order of 1. This one here has an exponent of 2. That means that the 0 at 0, 0 is order 2. Okay, we will do a few more of these, so it might take a little bit of time to sort of get used to everything here. We know this stuff. Okay, so I'm going to just draw a general sketch here, just try to kind of space things out equally. Doesn't have to be perfect, but... So we're going to plot the 3 x-intercepts at 1, 0, and 3. If I had a y-intercept other than 0, 0, obviously this is both an x and y-intercept, I would also plot the y-intercept. I'm going to make a little suggestion as to where my ends will start and finish here. So I think I will start somewhere here and end somewhere here. If I need to adjust them once I get to the sketch, then I can. But I sort of know that this has to happen because of my end behavior here. and then we're going to start sketching. Okay, so I have to use a little bit of like intuition and common sense here as I sketch. So first thing that I'm going to be approaching as I come from this end and I travel toward my right end, is I'm going to be approaching the 0 at 0, 0, and I know that this is order 2. Based on the information that we talked about above, I know that an order 2, 0 is going to come toward that 0 and bounce off of it. Okay, so as I go toward the 0 at 0, 0, lots of zeros, I will bounce off of it rather than going through it. My common sense tells me if I then have to go and cross the next 0 here, I'm probably going to have to turn the graph around, right? It's going to have to turn there. There's going to be a curve there somehow. And I know that when I go through this, it's going to be order 1. So I'm going to go right through the x-axis there. So turning and going through the x-axis. Okay, and then again, I have one last 0 at 3, 0. My intuition tells me if I sort of have to cross through this and end up here, I probably have to turn somewhere in between there, right? So we're going to turn toward 3. And I'm going through in an order 1 shape. So I want to just go right through it. And I will end where I expected to end, which is up in quadrant 1. Okay, Nicole, I'm guessing your question right now, how do I know how high and low the valleys and hills go here? Is that right? Oh man, I am so good. Literally every time I do this, that's the first question that's asked. So congratulations, you're that person that asked that question. I don't. That's what calculus is for, actually. So if you take calculus, you will know sort of like where these points are. One thing that I could do, if I really want to make sure that I have the correct like peaks and valleys, or like I have some information about that, is I could test these values in my equation and see the y that I get out. So I could, if I wanted to, I could plug in g at 2 and then see what I get, and I could plug in g at 0.5 and see what I get. That doesn't necessarily mean, like these mountains and valleys aren't always going to be symmetrical either. So it doesn't necessarily mean I'm going to get that perfect mountain peak or valley. I might have something that goes like this. That was a bad example, but I might have something that goes more like this. It's possible that that would not be symmetrical. So I don't know exactly where. I'm not saying at 2, this is going to be the turning point. I don't know. But I could test it if I really wanted to. I just want you to have some nice smooth curves in here, and I'm more concerned about plotting the information correctly than I am like this could have gone like this. I don't actually know. Maybe if my stylus would work. Hold on. Please hold. Okay, so I don't know. That could have done that. Could have. Maybe it was like that. I really don't know. Usually if you're like doing a turning point in between like 2 zeros, it does not go like particularly high. But again, I just want you to have the correct behavior as you go toward your intercepts, correct end behavior, and correct x and y intercepts. That's pretty much all I'm looking for. Okay? Okay, let's try another. Okay, so firstly, this is like kind of factored. It's in like that bracketed form, but it's not fully factored. It's also not in standard form. So if I want to determine degree here, I have a couple options, but probably the easiest option here is just to FOIL this out and see what the degree, the leading coefficient, and the intercept are. So I'm just going to do that above, and we'll factor more fully below. So FOIL first, outside, inside, last, taking it back to grade 10 again. So x squared times 3x gives me 3x cubed. X squared times negative 4 gives me negative 4x squared. Negative 9 times times positive 3x, negative 27x. x, and negative 9 times negative 4, positive 36. I might be able to sort of like imagine what this would be, expand it out, and probably decide on degree. But if you're not sure, just take a second and FOIL it. And in our next example, I'm going to show you a little trick if it's already like fully factored and it would be difficult to expand. But before we do that, let's talk about this example and the information that we know here. So degree, leading coefficient. From that, we can get end behavior. And from our standard form, we should also be able to get y-intercept to start here. Sophia. Okay. So we have degree of 3, leading coefficient of 3. This is odd end behavior with a positive leading coefficient. So here's what I know right away. Positive leading coefficient means that the right end must be going up, and odd degree, opposite end behavior. So left end must be going down. That's always the method that I use. Just leading coefficient's positive, oh, I know the right end's going up. Odd degree, so degree of 3, opposite end behavior. Left end must be going down. So this is 3 to 1, quadrant 3 to quadrant 1. What is the y-intercept here? Lucas?
36.
36. So I write that x is 0, y is 36. I can tell that by the constant. Or if I wanted to, in this format, I could sub in zeros for both of these x's and just calculate. Evaluate h at 0. That's what we do for y-intercept. Okay, we'll use that in a little bit. We need to get this guy fully factored over here. Not too much I can do with a 3x minus 4, but this is kind of a special type of quadratic that we learned about in grade 10, Oscar.
It's the one that makes like x plus 3, x minus 3.
Yes, so difference of squares is what we would call it. And when we have difference of squares, I have something squared minus something that's a perfect square. And when I factor this, I will get 2 brackets out of this. I will get a positive bracket and a negative one. And then I just square root each of these to find out the terms that go in here. So x plus 3, x minus 3. And then this one will still be 3x minus 4. I could also do like regular trinomial factoring with x squared minus 9. What I would be thinking of if I did regular trinomial factoring is I would consider that middle term to be 0. So I would be looking for 2 things that multiply to negative 9 and add to 0, which is positive and negative 3, and then they go into the brackets with the x's. That's why difference of squares ends up with that positive and negative. It's because we have a center term. The x term is like 0, has a coefficient of 0. Okay? All right, so now we're in fully factored form. Let's talk about the zeros and their orders. Oscar gave me 1.
1, 0, 0,
Negative 3, 0. What's the order on this?
That would be 1.
Okay. Order 1, and that is because there's an exponent of 1 on this bracket here. So remember, I'm getting negative 3 from this bracket, actually, because I switched the sign. And I'm getting the order from the exponent on that bracket, which is 1. What's the next 0? Billy?
Is it 3, 0?
It is 3, 0. Any idea?
Order 1.
Order 1. Perfect. And that is because, again, there is a 1 on this bracket. So that's where that's coming from. Okay, how do I get a 0 for something like this? 3x minus 4. Or what would that 0 be? Matashini? Yes. So if I don't know, what would cause this to equal 0, right? Because really I'm looking for where any x that could cause the whole function to equal 0. So that's what I do when I'm finding zeros. I'm looking for where each of those binomials is equal to 0. Let's just solve for what makes that happen. I move the 4 over, I divide the 3 out, and I get x equals 4 over 3. That's the x-intercept that gets produced by this binomial. The quick way is just switch the sign and do this number over this number. But if you're not sure, set that binomial equal to 0 and solve. And order on this one, Mathushini? 1. This one is also order 1. Great. So this is about like 1.3 repeated, 1.33333 forever. So I think I'm going to go by like, I don't know, maybe we can go by like 9s here. 9, 18, 27, 36 for the y's. And for the x's, I'll just go by 1s. That seems to be probably the easiest. And I know, so if we look at our end behavior up here, I know that I'm going to be starting down in the left end here, and I should be finishing somewhere up in the right quadrant here. Pencil them in lightly to start, and then you can always adjust them if you need to based on your sketch here. Okay, let's plot the x-intercept and the y-intercept. Y-intercept is up at 0, 36. X-intercepts are at -3, +3, and about 1.3 repeated, so maybe like right here, just estimate it. So I am starting in the left end down here, and as I come toward this 0 here, I know it's order 1, so I'm just going to go right through it as I come from the lower quadrant here into quadrant 2. Okay, I know that I'm going to have to eventually sort of come through this this y-intercept at 36, and I'll have to come down to the x-intercept at 1.3. So I don't know, probably something is happening in here where I have to turn and go down through 36 and head toward that next x-intercept. This is also order 1 as I'm approaching 1.3, so I'm just going to go right through it, like so. My intuition here is telling me if I have to finish over here and go through this x-intercept, there's probably a turning point in here, right? I'm just going to have to turn and curve, and this goes through an order 1 shape. So again, just flip it right up here and end in quadrant 1. Okay, so I have to sort of fill in the gaps a little bit here. It's kind of like connect the dots. We have to make some judgment calls and see sort of where we think it's turning. Again, do I know that this goes up above 36 here? Not really. Could I have drawn it more like this? Probably. Just as a tip for you, any degree 3 polynomial actually has to have point symmetry. We're going to talk about that in a little bit, but I know that all, like me, myself, you guys didn't know this as you were drawing it, but I knew that this had to have point symmetry, so I was just trying to make it kind of symmetrical, probably over like some point here. But yeah, you wouldn't have necessarily known that. Could this have gone like this? Could have. I don't know. Just make sure it looks nicely curved and make sure you go through all the points that you're supposed to go through and you have the correct ends. Okay, we're going to do one more graph here, and then we're going to do just a couple quick little questions here to wrap up. Can I answer any other questions on this one, by the way, before we move forward? Okay, last one. This is already in factored form for us. I want to teach you a couple of tricks for this, because who wants to expand something like this out? I don't really want to. That's going to take a while. I have to do this 3 times, and then I have to figure what that is. I have to FOIL this, and then I have to FOIL this with this, and then I have to bring the x in. I don't want to do that. Nobody wants to do that. Let's just figure out a couple little tricks here that we can use to determine degree. Firstly, because this is in factored form, let's just start with zeros and their orders. We can pick out that information here. So we'll start there, and then I'll talk to you about how we can do a couple little tricks here rather than expanding. Who can tell us the zeros and their orders? Or if you want, you can just give me one. Or you can give them all. Nicole?
I think one of them would be 5 and 0.
Close.
And 0 now.
What do I have to do if it's in the brackets?
Negative.
Okay. So -5 and 0. What's the order?
2.
Okay. Do you want to do more, or do you want to pass it off to someone else? Okay. Billy?
Positive 3, 0.
Mm-hmm. Order?
Order 2.
Perfect. Last one. Lexi?
Would the last one be just 0?
Mm-hmm.
The x-intercept, and then it would be order 1.
Order 1, correct, because I have an exponent of 1 on here. Perfect. In fully factored form, add up the orders on the zeros to get your degree. Okay, so all the orders should actually add up to the total degree if you have x-intercepts from all of those. So add up the orders of your zeros to get degree. So in this case, what is the degree? 6. So I do 2 plus 3 plus 1. Degree is 6. Perfect. Much easier than expanding this out. Okay, also in factored form. Okay, I'm saying this because I would not need to do this in standard form. Standard form, I just look at the equation and I can decide. For leading coefficient, so again, also in factored form, maybe I should just add that again so we're aware. In factored form, find the leading coefficient by multiplying all coefficients on the x's and applying their exponent. Okay, I'm also going to say also include any number in front of the equation in factored form. Okay, so what do I mean by this? Okay, so coefficients on x's are the numbers in front of the x's. Here is a coefficient on an x, -2. What's the coefficient on this x? 1. And same thing here. So I'm going to use -2 to calculate here. It will be -2 times 1, and I will apply any exponent. Whoops. I'll apply any exponent on the bracket for that. In this case, obviously, if I cube 1, it does not make a difference, but I'm going to do that for now just so we have that in our notes. And then times 1, the next coefficient on an x, squared. I'm going to apply the exponent there. What this does for me is it sort of does like how it would look in the expansion if I expanded it, but it does it like very quickly so that I don't have to expand to do this. So here's what I'm for this one, we will get -2. My stylus just stopped working again. Why does this keep happening? Come on. Just pop. If there was no x here, I still have to include any number that's in front. That's what I'm talking about with the also include any number in front of the equation, because that will eventually get multiplied into all of those brackets. So even if there's no x here, you still must include any value that is in front of those brackets in your calculation of leading coefficient. Okay? So make sure you apply the exponents on the brackets to any coefficients in front of x's. Okay. That was a long explanation, but once you get the hang of it, it's much quicker than expanding that all out. So if I know degree is 6 and leading coefficient is -2, what do we now know about end behavior? Lucas.
Quadrant 3 to quadrant 4.
Lucas says quadrant 3 to quadrant 4. Do you guys agree? Disagree? Everyone agree? Okay, I also agree. We have a negative leading coefficient. That means the right end must be facing down. And we have an even degree polynomial, which means we have the same end behavior. So the left end must also be facing down. Last one, y-intercept. The quick way to calculate this is, well, for this one, I actually don't have to calculate it. Why don't I have to calculate y-intercept? What do I know based on the information that I've already talked about here about y-intercept? Carol?
They all have x's. So there's no constant.
Not necessarily because, well, I guess, yeah, because we have an x here. There might not be a constant. Lucas?
Is it because one of the orders is 0, 0? So it's at the origin?
Yeah. So I already know the y-intercept because it's at 0, 0. So y-intercept must be 0, 0 here. If I didn't know that, I would just evaluate f at 0. So just calculate by subbing in 0 for your x's, you'll get your y. But yeah, Carol's right. If we were to expand this, we would have a constant of 0 as well. Okay, so let's plot 0, 0. I have one at 1, 2, 3, 4, 5, -5. And I have one at 3. 1, 2, 3. Here we go. So I'm going to adjust this end over here. Oops. I'm going to move this over a little bit too. Okay, so as we come toward 5, -5, this is order 2. So I know that as I come toward this, I'm going to bounce off the x-axis. My common sense here is telling me that if I have to go through this x-axis here at 0, 0, I probably will have to turn somewhere in between here. Okay, I don't know how high or low this valley goes. I just am trying to make some nice smooth curves here. This is going to be order 1, so we'll go right through it, like so. Maybe I went a little bit too high there. Go through it. Okay, and then again, I'm connecting the dots in between here. I'm probably going to have to curve somewhere in between there to finish off over here. And as I go through the x-intercept at 3, this is now order 3. What do I have to do? Yeah, it's going to have like a little extra S in there. So we're going to go through, I will turn and go through in like this S shape here. Okay, you might have to practice that a little bit. Oscar? Yep. Okay, so just make notes of your orders as you're sort of going through there. Any questions on this one that I can clarify? Okay, last couple quick things here. We are going to create a polynomial with degree 3 at zeros, with zeros at 5, 3, and 2. And it must also pass through the point 124. So we're going to create this in factored form because it gives us information about zeros. This would be very difficult to do if I were creating it in standard form. I don't even know how to do that. But factored form is much easier. So we can call it f at x, we can call it p at x, whatever you want. What do I know about the orders on all of these zeros if this is degree 3? Lucas?
They all order 1.
Yeah, yep, they must be order 1. If I have 3 zeros and the degree is 3, the orders must add up to the degree. They must be all order 1. Okay, so I know on the brackets I'll have 1s on exponents of 1s on all those brackets. How do I put in, because I have 3 zeros, I'm going to have 3 brackets here. How do I put 5, 3, and 2 into my equation to represent the zeros here? What should these look like? We're kind of like reverse engineering what we did like up in these ones, right? Lexi?
Well, you do like x minus 5, x minus 3.
Perfect. So we took care of those. This is going to pass through all of those. They're all order 1. So I don't need to write anything on the brackets. Here's the problem, 124. How do I make sure that this goes through 124? We will have some multiple out here. We're going to call it k for now. And we're going to solve for that by just subbing in the point. Okay, so all I have to do now is I'm going to evaluate when x equals 1, because that's what's given to me. And I'm going to plug in 1 for all the x's. So thinking back to like function notation in grade 11 here, and how we evaluate functions at specific values. What is f at 1 equal to? Can I sub something in for f at 1 here? In other words, I'm asking you, what is y when x is 1, Trent? 24, okay. Y is 24 when x is 1. So the function's value at an x value of 1 is 24. That's why I can plug that in here, right? F at x just replaces y. Remember that from grade 11? And then we're just going to simplify our brackets. -4, -2, -1 gives me -8k. Just multiplying here. And then divide the -8 out. Gives me k value of -3. You sub it back into the original equation with no points subbed in. You are quickly, I'm going to give you 2 minutes to create an equation that satisfies the next set of information. We are not going to sketch a graph. If you would like to sketch a graph just to practice, you can do that. I just want some options for different equations that we can have. So the only stipulations here, There is not just one right answer here, there are multiple right answers. The only stipulations is that it is only crossing at 5, 1, and -5, and it must be degree 5. So how can I create an equation that fits that information? You have 2 minutes, you can talk to a partner about it, see if you can figure out what that equation might look like. All right, anyone have an initial equation that they've made here? Trent, what is yours?
F of x is equal to x to the 4th power minus 625 in a bracket. And then another bracket, x minus 1.
So you are, so sorry, I'm just trying to think about this right now. X, okay, yes, but I want this in fully factored form, ideally, but interesting. I've never gotten that answer before. Let's just like, so that one's not fully factored, that one's like partially factored. Esther?
Bracket x squared minus 25, bracket closed, and bracket x to the power 3 minus 2.
So this is also not fully factored.
But if you just like x minus 5, x plus 5, and then x
So, Trent?
When you say fully factored, do you have to make difference of squares?
So you would have to, yours would have to be, use difference of squares, get that factored. There's a much easier way. Like you guys just made that way more complex than it needed to be. I need the 3 brackets to represent these, right, Lucas?
It wants to be like f of x is x minus 5 power 2, and then x minus 1 power 2, x plus 5 power 1.
Yes.
Do you need a k value though, or no? I guess
You could. You could have something out front, like I could have a -3 out front. I could have really anything. Or the k value, if I leave it, that means the k value is 1. So either one of those. So Trent and Esther, you guys are like kind of right, but you just made it a bit more complex than it needed to be. So keep it simple. What are some other options here?
I just have a question.
Sure.
Why is the exponent of 2?
So I need the orders on my zeros to add to a degree of 5. So any combination of exponents on those 3 brackets that add to give us the degree of 5 are totally fine. So what if I just switched? Maybe I put a cubed here, and then both of these are order 1. That's possible, right? I could have 2, 2, and 1 on any bracket. I can have 3, 1, 1 on any bracket.
do you put coefficients on the x's, or no?
No, only a number out here. So if I put a 2, that 0 is no longer positive 5. It's 5 over 2. So any value out front is totally fine. So if I put a 4 there, that's fine. If I can put a -4, I can put whatever. But don't put things in front of the x's other than 1s unless you have a 0 that is a fraction. Okay, so any combination, as long as you have those 3 brackets and you have orders or exponents on those brackets that add to 5. Okay, and you can have a number out front here, or you can just leave it as 1 by just leaving no number out front. All right. So we're going to continue